Hi guys, welcome to this lesson on testing for the convergence of a series. So we want to know, does a series sum up to a certain value or does it just diverge and go off? We're going to introduce you to two different methods for testing this, starting off with the integral test. So this is its formal definition. Feel free to pause the video right now and give this a read. Essentially what it's saying is that if the function of a series f of x is convergent, then the series is also convergent. And if the function of a series is divergent, then as you've guessed it, the series is also divergent. Now, it's important to remember before doing an integral test, you have to check that certain criteria are met. So the function f of x must be continuous, positive, and decreasing in the range that we have chosen. So for example, you can do the integral test on this function. It's positive, continuous, and it's eventually decreasing, which is okay. It doesn't have to always be decreasing, but as long as it's eventually decreasing, that's good. However, this function cannot pass the integral test because it's increasing. This one can't because it's negative at some points, and this one can't because it's not continuous. And that's really important to remember. Now let's go over three examples together so that you can get a better idea, and then I'll give you one to do on your own. So let's look at the series 2 over n minus 3 from n equals 1 to infinity. Can we check using the integral test that this series is convergent? Well, let's convert it to a function. So 2 over x minus 3. And does this pass the criteria? Well, 2 over x minus 3, looking at the denominator, this is undefined for x equals 3, because when x is equal to 3, this function f of x is going to be equal to 2 over 3 minus 3, which is 2 over 0. And that's bad, because that right there is undefined. We don't want that. So the integral test can't be performed on this function. Now, let's look at one that does work and what we do. So this series from n equals 1 to infinity of 5 minus 2 root n over n cubed. Does this converge or diverge? Well, it passes all the criteria, so let's convert it to this function. 5 minus 2 root x over x cubed. And here I just simplified it by splitting it up, because we're going to integrate, and it'll be easier to integrate this way. So let's integrate this function f of x between the limits we have here, so from n equals 1 to infinity. Okay, and it's going to be f of x, which we said is equal to 5x to the minus 3 minus 2x to the minus 5 over 2 dx. Now, this is going to be the same as the limit as t tends towards infinity as between t and 1 of 5x to the minus 3 minus 2x to the minus 5 over 2 dx. So here we just change the infinity sign to a t and just set a limit. I'm sure you've already seen this with things such as derivatives from first principle. It's just a limit. Now we're just going to do normal integration. So it's going to be the same as limit t to infinity. Integrate 5x to the minus 3. You get minus 5 over 2x to the minus 2. then you're going to get here plus 4 over 3x to the minus 3 over 2. And that's going to be between t and 1. So here again, you just plug in t like you usually would with integration. So limit as t goes to infinity of minus 5 over 2 t squared plus 4 over 3 t to the 3 over 2 plus 5 over 2 minus 4 over 3. Now, let's plug in the limit of t going to infinity. So when t goes to infinity, minus 5 over 2t squared goes to 0. Why? Because the denominator is approaching infinity. So anything divided by infinity is essentially 0. So this can be 0. This 4 over 3t to the power of something bigger than 1 also tends towards 0 because it's 4 over 3 times infinity sort of. So it's also going to be equal to 0. So it's going to be 0 plus 0. Then plus 5 over 2 minus 4 over 3. And this is going to just be equal to 7 over 6. So now we know that our integral of between infinity and 1 of f of x with regards to dx is going to be equal to 7 over 6, which means that this function is convergent. Therefore, this series that we have here is also going to be convergent. Now, we don't know to what this series converges yet, but we know that it's convergent. And don't make the mistake of thinking that it converges to 7 over 6, because it doesn't. This does not correlate to the sum of this. It just means that this function is also convergent. All right, that's great, good. So now I'm going to give you one example to do by yourself. You can pause the video right now and try this. The answers are going to be in a link in the description, so go look at that, and there'll be other problems as well. Now let me pass you on to my friend who's going to...
Hello. So now I'm going to talk about something called the comparison test. So just to jump straight in, so what the comparison test tells us is that, so for two positive series called An and Bn, if the sum of Bn converges, and for each n, An is smaller than Bn, then the series for An also converges. And similarly, if the series of Bn diverges, and if for each n, An is bigger than Bn, then the series for An also diverges. So this idea itself is a little bit hard to understand just on paper. So next, let's look at some examples and see when this is actually useful. So when is this useful? So suppose we have a sequence where An is equal to 2 to the nth power plus 1 under 1. And we want to know if the series of this sequence or this, either if it converges or if it diverges. And, because there's this 1 here, we can't use what we usually use to solve this. So what the comparison test tells us is that instead of looking at this, we can look at something similar, which we can actually solve to derive the answer to the limit of this. Now, let's try to solve for An equals to 2 to the nth power plus 1 under 1. And let's compare it to Bn, which is equal to 2 to the nth power under 1. And because we can tell that Bn converges, and if we do the calculations, it converges to 1. And also, we can tell that the sum or the series for n is bigger than 0 because an for each n, an is always positive. We can tell that the sum for an or the series for an is also bigger than 0 no matter what. Thus, we can write that the series for n is bigger than 0, and the comparison test tells us that because for each n, an is smaller than bn, then the sum will be small. The sum for an will be smaller than bn too. Thus, because this limit for the series for bn is equal to 1, the limit for the series for an will be smaller to that. Thus, we can get this, which tells us that an does converge to a number between 0 and 1. Hi, so then now let's talk about the limit comparison test. So what this test tells us is that, similar to the comparison test, if we have two sequences, an and bn, and they both have positive terms for all n, if we divide bn by an when we take the limit of both sequences, basically this, and it's equal to a finite number, which we will call c, then either both series, an and bn, converge or diverge, or basically they share the same property. So now let's just look at an example. Suppose we have a sequence of an, which is equal to this, and we want to see if whether an converges or not. Now, let's set bn, which we will use for comparison, to n to the third power under 1. And if we use this as with the limit comparison test, we can divide an by bn, which is this. And if we do that, we can get a number of 3 as our result. And because this is a finite number, we know that bn converges because bn is equal to n to the third power under 1. And due to the limit comparison test, we know that because bn converges, an has the same property, which means an also converges. So now let's compare the two methods we learned, the comparison test and the limit comparison test. So both methods are tests we can use to figure out whether an converges or diverges, where an is a sequence, which is a bit difficult to figure out whether it converges or diverges at first glance. And while the comparison test compares the values for an and bn to see which one is bigger or smaller to figure out whether an converges or diverges, the limit comparison tests use division to figure out the same thing. And that's the only difference. And you can use either method that suits you, and it will give you the same results. We just want to figure out whether or not whether an diverges or converges. And both results give you the same result. And it's up to you to use which one.